Now we're on to kind of a mixture of descriptive chemistry, kind of qualitative things, wonderful things about chemistry, as well as some numbers. So we're going to dive into kind of what an atom looks like. We're going to talk about those three subatomic particles: protons, electrons, and neutrons. And then we're going to talk about the concept of not all atoms of the same element look alike, and that kind of gets us to what we call isotopes, different isotopes of the same element. So what we know about an atom hasn't always been known. One of the things I just think is wonderful about science is that scientists build on what other scientists know. So for instance, back in 1803, Dalton came up with his atomic theory, and he said that all matter is made up of atoms. Now, he wasn't the first to say this. I think clear back in the BCs, was it Aristarchus came up with the concept of what an atom is, but he went ahead and came up with some basic kind of tenets of what he calls Dalton's atomic theory. Notice though that he really didn't know about the protons and the neutrons and electrons. So then, goodness, over 100 years later, we come up to Thomson. Now Thomson actually then, in 1904, you can see from the picture that now we have pluses and minuses. He said all matter is made up of these little balls we call atoms, and there are pluses and minus charges within that ball called an atom. And sometimes Thomson's model is called the plum pudding model because it's just kind of, how we say, kind of a blur of pluses and minuses. Now we know that that's not how kind of pluses and minuses, protons and electrons exist in an atom now. Then finally in Rutherford's, 7 years later, we have this purple model here. Now the reason it's kind of got dark purple and light purple, this dark purple is what we call the nucleus. And then the light purple around here is where the electrons are. So Rutherford said it's not like plum pudding. He said basically the positive charges are in the center and the negative charges, the electrons, are in a cloud outside the nucleus. So that's what Rutherford came up with. And we'll be talking more about the next deal. So if you compare Rutherford's model to Bohr's model in 1913, you can see what it's trying to show you is this electron cloud now. All the electrons actually are organized. And as I'm circling this, these are actually electrons. The electrons are organized with regard to energy and position. So the Bohr model kind of focuses on kind of some cool things that electrons do. All electrons around an atom are not created equal. We'll be talking more about those, where the electrons are. And then, last but not least, we have the Schrodinger model. And if you compare the Bohr to the Schrodinger model has kind of the electrons kind of in this kind of buzzy, sort of itchy sort of cloud outside the nucleus. So these little black dots is what we call the electron cloud, where there's a high probability of finding an electron at that energy level. So that's kind of the looking at the flow of what we know about an atom over time. So I think that is so cool. So Dalton's atomic theory, I'm going to kind of give you some basic tenets of Dalton's atomic theory. Now I hope you're not, I don't mean to pick on anybody, colorblind, but if you can see this blue text, okay, this blue text in the first few lines here I have on the slide is stuff that wasn't quite right. Okay, Dalton said that all matter is made up of atoms, which is exactly right. And he went on to say that these atoms are indivisible and indestructible. And I think I may have mentioned before, if this is the nucleus of an atom, and here's the electron cloud, you can actually, it's not this easy, but you can split the atom. That's called nuclear fission, okay? And so you can actually destroy an atom, okay? But, I don't know, didn't know about nuclear chemistry then. Another tenet of Dalton's theory says that all atoms of the same element are identical, says that they are identical in chemical properties, which is right, but he said that they are identical in mass, and that's not right, because actually in this part I mentioned we're going to be talking about isotopes. Okay, isotopes are the same element atoms of the same element with different masses because they have different numbers of neutrons. Okay. Dalton went on to say that atoms of different elements will have different masses and different chemical properties, and that is correct. What else? So Dalton's atomic theory went on to say that compounds, we've talked about compounds are where elements are joined together with chemical bonds between them in a known repeating unit, that compounds are formed by the combination of two or more atoms of different elements in a ratio of small whole numbers. Now, as I understand it, this actually is wrong. Okay, it's blue, it's wrong, because if you've done much with biology and studied, for instance, genetics and DNA and RNA, you know that they are very large molecules, and they have a very massive chemical formula. Then this last one actually has something red, and this red here in my notes means that if you go ahead and add the red, you are making his statement correct. So his original statement goes back to the first: atoms are neither created nor destroyed. And if you go ahead and say that, limit your manipulation of the atom to ordinary chemical reactions, that is correct. What's extraordinary chemical reactions would be that nuclear fission that I talked about. So it's true. Atoms can neither be created nor destroyed during ordinary chemical reactions. So kind of related to that last one, we have this conservation of fill in the blank. There's conservation of energy in our universe, but I want to talk about conservation of matter. It's kind of like what you start with can't just disappear, and you can't just out of nowhere get some stuff. So matter is conserved. We could say that atoms are conserved. We could say that matter is conserved. We could say that mass is conserved. Now this is all kind of qualified during ordinary chemical and physical processes. We aren't going to see, but if you've kind of dabbled in nuclear chemical reactions, nuclear fission or nuclear fusion, actually in that case, matter is converted to energy. Okay, so we're on to an assignment slide, and I want to put one more slide up here. This is kind of a repeat sort of thing. Remember that after Dalton's picture of an atom, then we get Thomson's picture. And now I'm seeing, I don't know, I'm just catching my eye. Notice here I spell it with a P, Thomson, and on my other slide I did not spell it with a P, so I think it is with a P. But anyway, this is showing you where we didn't necessarily know about the concept of a nucleus, where the protons and the electrons were just kind of intermingled in a plum pudding model.